ELEC2 2019 question 6, part A. The behaviour of a thyristor depends on the signal applied to the gate terminal and the voltage bias applied between its anode and cathode. The table lists 6 combinations of these conditions labelled A to F. Select the 2 combinations which cause the thyristor to switch on. Okay, so as far as thyristors are concerned, you need to know that there are 3 conditions for switching on a thyristor. I say 3, I suppose in reality you could say 2 as shown by the table. You need to know the voltage input and you need to know that then creates a current input and there's the bias. In short, you need to know these conditions, that the input voltage needs to exceed the minimum gate voltage. And this means that the input current needs to then exceed the minimum gate current, and normally they're connected, and your thyristor needs to be forward biased. Okay, so when we're looking at the possible inputs then, so we need this pulse of voltage to go in where the thyristor is also forward biased. So when you're looking down, C is obviously one of those conditions where you've got a positive pulse of voltage and it's forward biased. And when you look further down, E, and obviously with thyristor it doesn't need to remain high, the voltage, because the thyristor latches once you've exceeded this minimum gate voltage. So the answer for this particular question is C and E. Okay, B part 1. A high-powered DC load is controlled by a thyristor. The circuit diagram for the control system is shown below. Here is an extract from the datasheet for the thyristor. Now for this particular part, although this is what we call a commutator circuit, we're really only concerned with the left-hand portion of the circuit for this particular part of the question, because what we're doing is we're calculating the maximum resistance of R1, and that has nothing to do with the capacitor and R2 and switch 2. So what we need to do for this particular part is realize that these values within the table, 2 of them are important. And it's that minimum gate voltage and that minimum gate current, which is what is required in order to do the calculation. But before we can do that, what we also need to realize is that the voltage across that resistor is impacted by that minimum gate voltage. So the actual voltage across the resistor VR1 is actually going to be 24 minus that 1.2 required to switch on the thyristor. So in reality we've only got 22.8 volts across the resistor. Now we can actually work out the resistance of R1, because it's going to be its voltage divided by the current, and the current is the minimum gate current, and so it's 22.8 divided by 100 times 10 to the minus 3, and that gives us a value of 228 ohms. Now you might be wondering, what about the holding current, the 200 milliamps? Well, this is the current required to maintain the latched state of the thyristor once it's switched on. If you go below the holding current, or 200 milliamps for this particular thyristor circuit, then once you've latched the thyristor on, it will switch off if you go below that 200 milliamps. Okay, part 2. The graph shows the signals at points P and Q over a period of time. P is on the left-hand side of the capacitor and Q is on the right-hand side of the capacitor. And so the left-hand side is about switching on the thyristor, whereas the right-hand side in a commutator circuit is all about switching off the thyristor. And so that's hopefully what we're going to be explaining, because what we need to do is explain what is happening to the switches and to the thyristor at, and we've got 3 separate times, and each of these are worth 2 marks. So we've got a fair bit of information that we need to generate to get the 6 marks altogether. So at time 2 seconds, what's going on? Well, the thyristor is switched off and both switches are open. How do we know that? Well, we know that the thyristor is switched off at 2 seconds because the voltage at P is 24 volts, and that suggests that the thyristor has a large resistance, which means it's switched off. If it was switched on, then allow current to flow. It'd effectively have a very low resistance and it'd have a low voltage across it. And we can see that the signal at Q is also high, which suggests that the switch is open, it hasn't been closed. Okay, so what about at time for 5 seconds? Well, things change at 5 seconds because the voltage at P drops from 24 volts to 0 volts. That would suggest that the thyristor is switched on. The only switch that can switch the thyristor on to help us exceed the minimum gate current and voltage is S1. So that must have been closed. At the same time, S2 must be open because the way in which the circuit works is you've got to have S2 open and S1 closed in order to switch on the thyristor. Okay, what about for 10 seconds then? Well, because you can see at 10 seconds, the voltage at P goes negative. Now, the only way that can occur is if S2 has been closed and S1 is open. So this time it's S2 which is dictating what goes on, and it's the voltage at Q which is determining what happens to the thyristor. And what you get is the thyristor being forced into reverse bias. Now, the 3 conditions for a thyristor to conduct were exceeding the minimum gate voltage, exceeding the minimum gate current, but also the thyristor needs to be forward biased. So because Q forces the thyristor to go into reverse bias, it switches off. Okay. Part C. The triac is used to control the brightness of a lamp. Using a phase control subsystem, the circuit diagram is shown below. Identify component X and describe its function in this system. Well, I think most of us would be able to identify component X because X is a diac. But describing its function is a little bit more complicated. Now, there is almost a set answer that the exam board would give, and that's what I'm going to give here. And that is that the diac improves the rise time of signal triggering to reduce time on time, and it consequently reduces power dissipated in the triac. Okay, well, that's probably difficult to understand. What are they trying to say? Well, what they're trying to say is that the triac needs a minimum current to switch on, just like a thyristor. And the phase circuit can't produce a minimum gate voltage into the triac fast enough to produce a sufficiently big current. And that means that the triac is like in a semi-state of being on. Now, to get over this problem, because this basically means that you get power dissipated in a triac when it's in that phase of switching on, what you need is something which can fire a burst of current into the gate of the triac. And that's what the diac does. Once you get to its minimum voltage, what happens is it fires a burst of current into the gate of the triac. And what this does is it switches on the triac very, very quickly, therefore stopping it being in that zone where it's getting potentially hot and it's dissipating power. Okay, C part 2, another graph. Okay, so for C part 2, the graph shows the signal obtained at one point in the circuit. Which component does the signal appear across, And then for the second part, explain what is happening to the triac and to the lamp. And we've got 2 points. We've got to explain what's going on between points P and Q and between points Q and R. So let's deal with the first part. What is this graph? Which component does this signal appear across? Well, this is the triac. And we can tell it's a triac, but a very quick way of being able to establish that. This is that it's got both positive and negative voltages. And the triac, remember, works in both the positive and negative direction. Right, okay, so for part 2, explain what is happening to the triac and to the lamp between points P and Q. And hopefully this will explain why this has to be the triac and not the whatever it's attached to. Okay, so between P and Q, the triac switches on and latches at P. So what we've got to remember is that we need this minimum voltage in order to switch on the triac. And so before then, it just follows the voltage of the supply, which is why it's just rising before it gets to point P. But immediately it gets to that switching voltage, it switches on. And when it switches on, what happens is the lamp is going to be lit with a voltage that follows Vs. Right, so all of the voltage goes to the lamp, and all of that voltage is dictated by the voltage of the supply. Okay, what about between Q and R then? Well, between Q and R, it's the triac working in the opposite direction. Now, triacs are designed to do that. Again, it will follow the voltage of the supply, but the triac and the lamp are both switched off because it hasn't exceeded the voltage required to switch it on. That concludes question 6.